begin with a word of prayer. I'm sure that thing is working. So let me begin. Dear Heavenly Father, we thank you again for this class. I thank you for this day we have just to study your creation. Help us to use this time wisely to review for the test tomorrow, just to resolve any remaining questions. Lord, in your name I pray, Lord Jesus. Amen. All right, so let's see here. We can look. Well, I guess most of you have probably looked at this, if you could read between the lines of my cryptic message yesterday. But I realized that the solution had already been posted several hours by the time I sent that announcement. I'm like, well, I didn't know for sure one of you hadn't seen it already, so because all of you are just like sitting at Canvas going, what did he post just now, you know? But just to be err on the side of caution, I sent that cryptic message so that you'd see this. All right, so in polar coordinates, in polar coordinates, it's very simple, right? Like this region has an inner radius and an outer radius, inner radius 1, outer radius 2. So in polar coordinates, the setup is very simple, right? 0 to pi, 1 to 2, like that. In Cartesian coordinates, on the other hand, you have to split into these 3 different regions, right? Because there's a different top and bottom. If you, I don't know which way I did here. Yeah, I did a type 1 setup, right? So the y is bounded by 0, and then the outer circle for the outside edges, but it's bounded by the inner circle and the outer circle for the inside region there. So that's why you need 3 parts. Of course, by the symmetry here, you probably could just break it up into 2 and like double 1 or something. But anyway, there's that. But just to recap, to calculate the centroid, we basically calculate the average of x or the average of y over the region, and the average of x comma the average of y is the so-called centroid. Let's see here. This one, as some of you realized pretty early on, you can't integrate sine of y squared, so you need to set this up so that it's a type 2, I guess. So x goes from 0 to y over 3. And so when you do the x integral, it pops out a y over 3, and then all of a sudden you can do u substitution, and yay, answer. That's a pretty standard test question right here, all right? In fact, this is, for the most part, an old test that my brother once gave. So this once upon a time, this was a test for Calculus 3. This part of the material, at least part of this. I had to chop it up a little bit. His course doesn't quite follow in ours. Like I don't think he has 4 tests, for example. Anyway, this one here, I make a u equals to, well, it tells you, doesn't it? In the problem statement, I think it told you to make the substitution u equals to that, v equals to that, right? And so with that in mind, we have to track what happens to the, so how do you track, so like the box change of coordinates is a quote-unquote linear change. So whenever you have the new coordinates depend on the old just according to like, you know, multiples of the variables plus a constant, that's a linear change of coordinates. And here's a fact for you. Linear changes of coordinates take lines to lines. So if your integration region is also defined by lines, all you have to do to understand where it maps to and the exchange of regions is just to follow which line goes to which line. How do you do that? Well, you take the given bounds, in this case, you know, y equals x minus 3 and y equals x minus 4, and you just sort of convert those to the corresponding bounds in u and v by plugging in the formulas, basically. Now, I can't just plug the formulas in for that because I have to solve those for x and y, right? So if I solve those for x and y, well, I mean, either you can solve them for x and y, or you can, I don't know, I forget exactly how it goes in here, but after the dust settles, this is what the integration region looks like in the UV coordinate system. So it's nicer, and but it's still interesting, right? It's still a type. You want to set it up type 2, so like you've got your right v and your left v and your maximum, your minimum. Excuse me, my bad. Your right u and your left u. This is uv, right? So usually we do like left x, right x, but this is x is u and y is v, quote unquote. Anyway, the integration sets up like this, and that's how that goes. Let me skip ahead here. This one is pretty much just yells at you, use cylindrical coordinates, right? So in cylindrical coordinates, that is, z is going from r squared plus 1 to 5. R squared plus 1 is the bottom, 5 is the top. The radius is sweeping from 0 to 2. 2 is the biggest it gets at the intersection of the paraboloid and the plane, happens at r equals to 2. And theta, there's no dependence on theta, so we do a full sweep of the theta, and that's how that goes. Remember that the dv, we've got the r dz dr d theta because the r from the cylindrical Jacobian appears there. Let's see here. Problem 5. We got, so this one is just about setting up, and it's a good problem. So we have to interpret what does the original problem mean. So like the original problem, we've got in the inside integral, that's concerning dz, right? So we've got 0 is above z, and minus the root 49 minus x squared minus y squared is below z. So that means that we're like in the lower half of a ball, right, of radius 7, centered at the origin from the look of it. If you set z equal to the square root of 49 minus x squared minus y squared, you get x squared plus y squared plus z squared equals to 49, which is a sphere of radius 7. Well, it's a ball, I should say, right? So you're in the lower portion of a ball, and let's see here. The y is sweeping the full thing, right, from the square root to the minus the square root. So the y is going completely, but the x, the outer x, only is going over the negative half. So it's only a quarter of the sphere, actually, right? Because it's the lower half, and of the lower half, it's only 1/2 of the x. So let's see here. When you draw the picture like that, that says, let's see here, let's think about it. The theta for that is sweeping what? It's missing 0 to pi, right? So we need to sweep from pi to 2 pi, for instance, and the colatitude, it's below the xy plane, so that would be pi over 2 to pi, which is why what we have here is 0 to 7, pi over 2 to pi, and whoop, wait a minute. Hold on a second, what have I done? Hey, is that picture not how I draw it? Oh, that picture's not how I draw this stupid thing. Well, that's very unhelpful. Dude. I don't think, I mean, yeah, that's not how I would draw that sphere. That's not my standard picture. Well, beggars can't be choosers. I mean, this is a solution that my brother typed up, like I said, and I don't know why he would, I mean, maybe it's a question of perspective. I mean, there's tech code that creates that diagram, so, props. It's impressive. This is not an included picture. It's something that's generated from like Tixie or something. I wish I had that much time. But it's okay. I probably still would just look up videos of spinning rats or something. But so a better picture, a picture that would be in concert with my usual arrangement of things. So we have x is negative, right? So that puts the sphere, or the quarter sphere, back here. All right, like back here. And so we're sweeping from this right here is pi over 2 equals to theta. This guy over here is 3 pi over 2 is theta, right? And so like this is all behind the zy plane, all right? And so that's why I was not looking at the body of the text. I was just believing the picture, which is wrong. So wrong from my perspective. I mean, you could draw axes on that to make it correct, right? But anyway, I mean, in my brother's defense, he actually didn't put the axes in there, so I can't really fault him, you know. And he is left-handed, so maybe that's how a left-handed person would draw it. I don't know. Anyway, any questions about this? Notice the cylindrical coordinates in the middle. The theta is the same sweep, right? The radius is the same, like it's going out to a maximum of 7, but the z is interesting, right? How do you find this formula for z? It's not complicated, right? The bound right above it. Well, of course, this is that's the y. That's the y bound, right? Excuse me, up there is the z bound. You see that? That's the one to look at. There's a z bound. So, and this is also the innermost. So if logically it probably has to match that since it's the same initial cut. That doesn't have to be true, I should say. But anyway, it does correspond geometrically to that one right there, and x squared minus y squared is r squared, so that's just directly 49 minus r squared. Does that make sense? The bottom of the sphere has the equation z is equal to the square root of 49 minus r squared. So minus the square root, so that's why that's there. All right, let me go on here. Cones are nice. Cones are nice in spherical coordinates. Y is now. Hey, look! Now this picture agrees with my usual interpretation of x and y as it relates to the presentation of three-dimensional solid things. Right? That is my y greater than or equal to 0. That would be my typical picture. Funny. And z equals 18 is the top of that. So if I look at that, my theta is sweeping from 0 to pi, and the colatitude is sweeping from 0 on the the axis of the cone down to whatever the colatitude is of the side. I don't know what that is right offhand. Oh, but you've got z is equal to what? You see that? You've got z is 2 times the square root of x squared plus y squared, right? So, all right, well, z is also equal to rho cosine of the angle, right? And what is this? That's r, right? But that's 2 rho sine phi. Of course, you could also just you could figure out the angle with geometry just the same. But here's how to do it with algebra. Some of you like algebra more. Some of you like geometry more. These both matter. The rows cancel, and we've got that the tangent of phi is apparently 1/2. So the phi that we sweep to is going to be inverse tangent of 1/2, right? I don't know if that's a nice angle or not. That should be relevant for part C of the question here, right? So in rectangular coordinates, well, anyway, any questions about this one? I don't want to belabor it. Okay. Okay, so he just leaves it as arctan of 1/2. Great. It's been a little bit. It's been a minute since we did this, but this is half the, well, probably a third of the test more. It depends. It could be up. It's between a third and a half. It kind of just depends on how things go. But I usually make the test more integration because I think that's more of the effort. I mean, I know you've had a whole homework on differentiation, but you'd probably rather not I make half of the test optimization anyway, because I think that's much more dicey, right? If you're given an integration, as long as it's not something truly like hideous, you've got a decent shot at doing it, especially if it's something like integrate over a ball or integrating over a part of a cylinder or a cone or something. Now that you have got your feet under you about like how the different coordinate systems work, you've got a pretty good chance at those if you just do the integration and mind the Jacobian factor. But admittedly, these optimization problems, they do always come like packaged with some algebra that you might or might not get stuck on, right? I don't know. Each of these problems have their own kind of trouble. This one here, we've got this cubic minus x cubed plus 12x plus y cubed minus 3y. So to start with, calculate the gradient. There it is. The Hessian, like I told you guys, is this 2 by 2 matrix, which works out to that. And we're supposed to find the quadratic approximation of it at 1, 2. The quadratic approximation we get from the value of the function plus this is the first three terms are just the equation of the tangent line, right? And then this is the quadratic approximation correction. I think in my notes I tend to call Q just the last piece, right? So my notation differs a bit here with his Q of xy, but that's not a big deal. Anyway, there's the formula for it. So we're supposed to find the critical points. How do you find the critical points? Well, you want to set this equal to 0 and that equal to 0, right? So 3y squared minus 3 equal to 0 has solutions y is plus or minus 1. 3x squared minus 3x squared plus 12 equal to 0 has solutions x squared equals to 4, x equal to plus or minus 2. There are 4 critical points. X equals to 4, y equals to 3, plus or minus on both of those. The plus and minus not connected. There are 4 critical points, I believe. Oh man, I did it wrong. 2, plus or minus 2. X squared equals to 4 gives me x is plus or minus 2. And then what does he do? Well, you need to check the determinant. So we call the determinant the big D. Oh man, doesn't he? I'm sorry. Well, I usually say big D, right? Is the determinant of what he calls the Hessian. It's what, fxx, fyy minus fxy squared. And so if we look at big D of 1, 2, big D of minus 1, 2, big D of 1, minus 2, big D of minus 1, minus 2, what happens? Where is my big, what is big D? Big D is, oh, the Hessian's constant at the point where, no, excuse me. Part B was for the point minus 1, 2. We're now where? We're now at these points. Oh, he had us find the quadratic approximation at the at one of the critical points, didn't he? Yep. Okay, so I'll get it eventually. The determinant of that is 72. So at 1, minus 1, 2, 72, of course, that's positive, right? What does this work out to? Can you guys tell me? I can't see it in this wall of text. I should just go up there. What's fxx? Oh, it's right there. I'm sorry. Minus 6x. So we've got minus 6x times 6y, and the xy term is 0, right? So my Hessian is minus 36. I mean, see my determinant, big D, as the usual books call it, minus 36xy. So it's if the components of the critical number differ in sign, it's positive, and if they are of the same sign, it's negative. So what does that mean? That means that 1, 2, and also minus 1, minus 2 are saddle points, right? They have negative big D, which means they're neither a max nor a min. It's like a saddle. And the minus 1, 2 and 1, minus 2, those are possible min-maxes. Which are they, min or max? Well, it depends on fxx, right? Well, fxx is minus 6x, and if x is positive, it's negative. So that would make this one has fxx equal to what? Minus 6, is it? Yeah, and so that's less than 0, so therefore f of 1 minus 2 local what? Local max, right? And similarly, and of course f of 1 minus 2 is did I do it? Did I do it?
Isn't x supposed to be the 2's?
What happened?
Like why you have 1, 2, but he has 2, 1.
Oh, have I done that? Oh, stink. Sorry. Well, I was thinking maybe he made part B interesting, you know, in the sense that he'd already had you guys find the quadratic approximation at critical point, but I guess that wouldn't be interesting. Why? That wouldn't be interesting because then the linear piece would be 0, and so you wouldn't learn as much about your students if you made the linear piece 0, right? So my bad. So that one is supposed to be negative, positive, positive, negative. All right, so now I'm supposed to look at f of, good grief. Well, anyway, let me erase before I will forget to erase one of my mistakes, and then it'll be bad. So let's just erase the whole thing. Not the whole thing, just this piece. All right. The point is, saddle, saddle. These are min-maxes, but the one with x equals to 2 has fxx, which is minus 6x equals negative, so that's a local min. Excuse me, local max. If the second derivative is negative, it's a local max. This one has the second x derivative positive, therefore minus 2, 1 corresponds to a local minimum, right? Anyway, so it's all here. Yes, thank you. I do this sort of thing. I'm sorry. I don't mean to switch things around like that to you. All right, so suppose f of xy is a nice function with continuous partials of all orders, and you're given that the quadratic approximation is this, right? And what are you supposed to say? Is it a critical point? What's the gradient? What's the Hessian? As I introduced you, Hessian's just a quick way of packaging all of the second partial derivatives in one nice bundle, a 2x2 matrix. But listen, you don't have to learn the Hessian. I don't expect you to use the Hessian on the test or anything. If you do, I'll know what you're talking about because we had this conversation, right? But you can just use, it's more likely on my test that I ask you to find all the second partial derivatives, given that that's the multivariate power series expansion, right? That would be how I would ask that. But it's the same, right? Because this says fxx is 8, fyy is 4, and the mixed partial derivative is minus 3 at the point in question, namely 3 minus 2. So is it a critical point? Yes, because the gradient's 0. What kind of critical point is it? Well, the second derivative is positive, and the determinant of this, or the big D as we call it, is 32 minus 9. And that's positive, so therefore, yeah, it is a max min. And again, it's a minimum because the second derivative is positive, so that's the second derivative test. This next one here is not a critical point because it's got a, what? It's got a term that's linear. That corresponds to the gradient being 5, and the x derivative is 5, and the y derivative apparently is minus 1. And where are we centering? We're centering at minus 1, 0, because you're looking at powers of x plus 1 and y. All right, so working backwards, it's the quadratic approximation at minus 1, 0. And so it's not a critical point. And if it's not a critical point, then you can't you can't really decide whether it's a max, a min, or saddle, or anything like that. All right, it's irrelevant. Although he did leave a spot for us to put the linearization, right? There's the linearization is just everything up to, but not including the quadratic terms. Method of Lagrange multiplier. This is a nice Lagrange multiplier problem. Usually, when you're constrained to a circle, it works out pretty nice. So you just, what do? You calculate the gradient of f, and you set it equal to lambda times the gradient of the constraint. That gives us, these equations. I'll write them out here. It gives us what? It gives us y squared equals to 2x lambda, and it gives us 2xy. Yeah, 2xy equal to 2y lambda, right? So these are your, and of course you're also subject to what, x squared plus y squared equals to 12. And so you got to solve these three equations and three unknowns simultaneously. And that's done here. And what happens, let's see here. Solve for lambda is what you guys did? See, like lambda is equal to y squared over 2x, which is equal to 2xy over 2y. The y's be canceling, and the 2's be canceling. So this is what? Oh, that's x. Oh, that's nice. X equals to lambda. Huh, that's cool. If x is equal to lambda, then we've got y squared is 2x squared. And then you just take that, shove it in over here, and then you've got just an equation just in y squared, which you can solve. Right? 2y squared equals to 12, which is y squared equals to 6, which gives you y is plus or minus root 6, if I did it right. Maybe. Maybe not. No, I did something wrong. Y squared. Oh, 2x squared. You get 3x squared. 3x squared equals to, 3x squared equals to 12, which gives me x squared is equal to 4. Is that right? So x is plus or minus 2. And if x is plus or minus 2, y squared is 8. So y is plus or minus root 8. And then you just plug in these 4 different cases and see which is max, which is min. You know that the max min exists because a circle is compact. So you're guaranteed that the method of Lagrange multipliers works, right? The other thing is you might worry about dividing equations, but you don't really need to, because notice that the constraint equation is a circle, right? And you can't have both x, well, you could have x equal to 0 on that. Rats. I'm wrong about that. I was thinking I can't have both x and y be 0, though. So, I don't know. As a general point of order, I divide things, I look for solutions, and then I ask myself, have I missed anything in my division? You know, so technically speaking, as soon as we divide by something, we should set out a separate case that that thing could be 0. And then usually what happens is if you assume the thing that you divided by is 0, it forces something else to be 0, and then once that other thing is 0, then you get a contradiction for your constraint equation. That's usually what happens, but anyway. All right, so last but not least here, I just put the blank. This is just the blank thing you guys filled out, okay? But at the end of it, I have some work here to share with you. So like so this one, I messed up. The reason I messed up was, in order to make this a fair question, I have to have x, y, and z all appearing non-trivially. Otherwise, I don't know what happens, because the lack of an x means that something interesting could be happening in the x, either in the positive or the negative sense. It could turn it into a saddle, or a max, or a min, or a parabolic. I don't know. So the question is ambiguous, as stated, except that that is the 6th order approximation. That much I'm pretty sure. Okay? That's fine. But the classification of the critical point, it is a critical point too, that's also clear. The nature of the critical point is not clear because I didn't give you enough. Now, if I had take the example I have and like add 3x squared, just add a 3x squared at the start, then the approximation at 0, 0, 0 would be 3x squared plus y squared plus z squared. And if I have something like that, well, if I just have a sum of squares, then what happens is you go away from 0, 0, 0. Well, you're definitely adding values close to 0, right? So that makes 0, 0, 0 a minimum, right? On the other hand, if all of these were negative, it would be a maximum. If one is positive and one is negative, or if one is positive and 2 are negative, or if they're different signs, the quadratic terms at a critical point, then you can be assured it's a saddle point. Although, don't ask me to graph it in 3 dimensions, yeah.
I think it works out to being a local minimum along x equals 0. So it's like, it doesn't decrease in x. But it's because that one line is.
A local minimum along x equals, yeah, again, I'd have to, you might have found a better analysis here, but with the simple, here's my test question you can solve in 2 minutes logic, it's not fair. And it is a 2-minute problem. That kind of problem is a 2-minute problem because all you literally have to do is find the power series expansion, examine the quadratic terms. If they're all positive, it's a minimum. If they're all negative, it's a maximum. If there's a mix of positive and negative quadratic terms, it's neither a min nor max. That's it. That's the naive second derivative test for higher derivatives. Only for 2 variables can we deal with the mixed derivative case because we've got this determinant of the Hessian which takes care of rotated things that we can't. We need linear algebra to do it for more variables. This one here, yeah, I can see why you guys couldn't do the integral because it's like, what is it like? It's if you do it directly, then if you use spherical coordinates, your equation for the plane is this, and then you end up with like a cube of that, right? Which you probably can't integrate. So the trick here, and I haven't talked enough about this trick admittedly, but here I am, 2 minutes before the end, pointing out that first of all, you can calculate the volume. I need the volume to calculate the centroid, right? Because the centroid is the average of x, y, and z. The average of x is the integral over x divided by the volume. Integral of y divided by volume is y bar. Integral of z divided by z, the volume is z bar. So I need the volume of the region to calculate the integral, to calculate the averages. And the volume actually is pretty easy to calculate in the sense that what I do is I just break it into 2 pieces. The, the 4-sided triangular thing minus the 1/8 of the sphere, which is cut out. So just subtract off the volume of the 1/8 of the sphere, which is missing. Yeah? And so there's the volume. It's 1/6 of 64 minus pi. And then just be sneaky, define E tilde to be the basically the region union to the cutout piece. Then that's a nice rectangular region that you can integrate. So I calculate the integral of x over that full region, and then I just subtract off the integral of x over the bumped out, the part that's been cut out, and do the integral. That integral you can do, believe it or not. It's not entirely trivial, but it's actually not that bad. I was a little bit worried when I had I had a cosecant to the 5th at one point, and I was like, uh-oh. But then I realized that I also was multiplying by sine cubed, and then all of a sudden it became a cosecant. It became a cosecant squared, and then I was like, oh, well, cosecant squared, that's not bad. Although that's not this problem. I'm getting ahead of the story. That is actually, so yeah, by symmetry, that's where the centroid is, I believe. And over here, this one was the one that had cosecant to the 5th in it. But it's multiplied by a sine cubed, which made it a cosecant squared, which makes it not too bad. But that actually can be calculated as well. It's just hard. Anyway, I will post this into Canvas. See you guys tomorrow.